we'll talk about normal extensions. These play an important role in Galois theory, which is where we are eventually headed. So let me make the formal definition first, and then I'll make some remarks about it. So let K over F be an algebraic extension. So F is fix some base field F and take an algebraic extension of F. Be an algebraic extension. Okay, we say that K is a normal extension. So we say K is a normal extension, or the extension K over F is normal if there exists a collection of polynomials. So if there is a set, if there exists a, let's call it a collection, Fi of x, I running over some index set, so it could be an infinite collection of polynomials. There exists a collection of polynomials with coefficients in Fx. So this subset, this collection Fi of x is a subset of Fx such that K is the splitting field of this collection. Okay, so that's the definition, but let me just say what I mean by the splitting field of a collection. We talked about the splitting field of a single polynomial. So the splitting field of a collection means that each Fi splits over K. So recall there were two properties for a splitting field of a single polynomial. So similarly here I have two properties. Let me now call them capital A and capital B. Each Fi splits over this field K, and it splits completely into a product of linear factors, and property B says that this does not hold for any proper subfield of K. Okay, if E is a proper subfield of K containing F, then at least one of the Fi's does not split over E. Okay, so then there exists at least one Fi, there exists I in I such that Fi does not split over this field E. Okay, so that's what we mean by being the splitting field of the entire collection. Okay, so just like what we did earlier, so remark, we can replace this condition B, remark as before, the splitting field of a single polynomial. We can replace B by the equivalent condition B dashed by the equivalent condition, let's call it B dash again, capital B dash, which says that K is generated. So the subfield of K, the subfield of K generated by F, and the roots of all the Fi's put together. So the roots of all the Fi. Okay, this subfield coincides with K itself. It's not a proper subfield, but in fact the whole field. Okay, so and I will sort of leave this proving the equivalence of B and B dashed to you. It's along the same lines as what we did earlier for a single polynomial. Okay, so here are some examples. So if I take F to be the field Q and I take K to be the field which is Q adjoined with two elements, one of them is root 2, the other is I. Okay, then this is a normal extension. So claim is that K over F is actually a normal extension, and to prove this I have to exhibit a collection of polynomials for which this is the splitting field. Okay, And here it sort of, I mean, if you look at the elements we had joined, root 2 and I, it sort of tells you what the polynomials should be. So let's take the polynomial fx equals x square minus 2, and so let gx be x square plus 1. Okay. So the claim is that k over f, k is the splitting field of this collection fg. So claim is that k is the splitting field of the collection, well, in this case just two elements f and g. Okay, so let's just verify the two conditions quickly. A, both of them should split over this field. Okay, that's fairly obvious, because over this field f splits as x minus root 2 into x plus root 2, and both minus and plus root 2 are in this field. Gx similarly splits as x minus I into x plus I. Okay, and again it's easier to check b dash in this case rather than b itself. So what b dash says is that if you take this field q, so okay, what's this field k that we are talking about? Q of root 2i, and we have q here. So what it says is, if you consider, so this is your k, this is your f, you take the subfield of k, which is generated by q together with the roots of all these polynomials. So what were the roots? They were plus root 2, minus root 2, I and minus I. If you adjoin the roots to q, you take the subfield generated by this, then it should give you all of k. Okay. In this case, that's fairly obvious, because as soon as you adjoin root 2 and I, you get everything. Okay. So this is in fact k. Okay. So we have checked condition b dashed also. So this is an example of a normal extension. Okay, now this is a slightly unsatisfactory state of affairs, because to check or verify that something is a normal extension, what you have to do really is to hunt for some polynomials, right? You have to find a collection of polynomials for which this is the normal, I mean, for which this is a splitting field. Of course, in practice, that is how we will construct examples, right? You pick some polynomials and look for sort of the splitting field of that entire collection. But sometimes we want a more intrinsic characterization, meaning without having to look for those polynomials, maybe in terms of other sort of abstract characterizations, and this is sometimes useful. So let me just formulate this characterization as a proposition. So it says, let k over f be an algebraic extension, be an algebraic extension. Okay. Then the following statements are equivalent. The following are equivalent. Statement 1 says this extension is normal, k over f is a normal extension. So being normal means, of course, that it is a splitting field of a collection of polynomials, but the other additional thing I am talking about is point number 2 here, which says that if L is an algebraic closure, so you take an algebraic closure of k, if L is an algebraic closure of k, okay, and phi from L to L is a field automorphism, is an automorphism of L such that when you restrict it to the base field f, you get the identity. Okay, so this, by the way, this sort of thing keeps occurring all the time, and we usually give it a name. So we say such a map is an f automorphism. So putting the f in front just says that it acts as identity on f, or it fixes f pointwise. Okay, so given an f automorphism of the field L, we have, so if L, sorry, let me read this again. If L is an algebraic closure of k and phi from, maybe I should rephrase it a little bit. So let me say, let L be an algebraic closure of k, then for every automorphism, for every f automorphism of L, we have the following fact, that phi of k equals k. So probably you should just do this on the next page. So let me say for every f automorphism we have phi k equals k. Okay, so every f automorphism of L always preserves k. That's the statement we want to make. Okay, and fact 3 says that for every alpha in k, take any element of k. So this statement doesn't involve the algebraic closure. For every alpha in k, the minimal polynomial m alpha of x. Okay, this is a minimal polynomial. This is a minimal polynomial of the element alpha over the field f. Okay, the min poly m alpha of x splits completely over k. Okay, so this is saying that if you can show that your extension is normal, that is, if you can exhibit one set of polynomials for which it's a splitting field, then in fact no matter which alpha you take from your field, its minimal polynomial will also split completely. In some sense, it's a splitting field of every element. If you can just take the entire collection. Okay, so I mean we are going to do that in just a moment. So let me prove this. So these are three equivalent characterizations. The second characterization is in terms of homomorphisms. Okay, so let's prove. We'll prove it in the following way. We'll show that 1 implies 2 implies 3 implies 1. Okay, that will show equivalence of all the statements. So let me start by showing that 3 implies 1. So suppose I know this, that for every alpha in k, the min poly of alpha over k splits completely over k, and now I need to show property 1, which is that k is a normal extension of f, which means I must exhibit a collection of polynomials for which k is the splitting field. So now here the collection of polynomials is obvious. Okay, so consider the collection of polynomials, consider the collection, just take the minimal polynomials m alpha of x for every alpha in k. Okay, this is a very large collection, if you will, of polynomials with coefficients in f. Okay, clearly k is the splitting field of this collection. Okay, meaning when I say clearly, of course I mean assuming 3. So maybe I should say clearly, if I assume 3, then it implies that k is the splitting field of this collection. Okay, why? I need to check two properties, that every polynomial in my collection splits, that's what 3 says, and the fact that it is a splitting field says that if I take f and take the roots of all these polynomials, the field subfield they generate should be the whole field. But remember, alpha is the root of m alpha of x, right? So what I am doing really is, to f I have to adjoin every single alpha in my in k. So of course when I adjoin every alpha in k, of course I am going to get k. Okay, so this is sort of the trivial direction. It says that if you have this entire collection of minimal polynomials splitting over k, then definitely it's a normal extension, because you can take that whole collection as your collection really. Now let's show 1 implies 2. So this means that I am going to assume 1, that it is a normal extension, meaning there exists a collection for which it is a splitting field, and I will prove 2, which is that any homomorphism of the algebraic closure will have to preserve this subfield k. Okay, so let's start with the definition. Let fi of x I ranging over some index set, subset of fx, be such that k is its splitting field, such that k is its splitting field, and what are we supposed to? We are supposed to take an algebraic closure. So let's prove 2 now. To prove that, we'll start with an algebraic closure. So let L be an algebraic closure. Of K, and let's take a automorphism of L, okay, which is identity on F, be an F automorphism. Okay, now we just need to show that phi of K is K. Okay, now need to show phi K is K. So this sort of argument already appeared. In fact, we need to show E equal to K. So this sort of argument already appeared when we were proving uniqueness of the splitting field. In fact, it's exact same argument. So let's just quickly repeat it. So what's the argument? K, recall, is nothing but the subfield of, well, of itself, if you wish, or the subfield of L, which is obtained as follows. You take F and it is generated by F and the zeros of all these polynomials. So maybe I'll just write it in words. K equals the subfield of itself or L, it hardly matters. So K is nothing but the subfield of L generated by F and the roots of all the Fi's put together. Okay. But we observed the following statement, that in the proof of the uniqueness of splitting fields, that if alpha in L is a root of Fi, then phi alpha is also a root of Fi, is a root of Fi. Well, in this case, again in L. Okay. Why is that? Because, I mean, in the earlier proof it was L and L dash when we were trying to show uniqueness of splitting fields. Here it's an automorphism. Both sides we have L. So if alpha is a root of phi of Fi, then when you apply phi to it, it continues to be a root of Fi. Okay, again in L. And why was this? Because the map phi was identity on the base field. It was identity on the coefficients. So you concluded that phi alpha is again a root. So what does that mean? It says that since K is just the subfield of L generated by F and all the roots of the Fi's, when you apply phi to K, okay, which means you have to apply phi to all the roots of all the Fi's and see what you get. But the roots of Fi's under phi map again to the roots of Fi's. Okay, so phi sort of preserves the set of all roots of all the Fi's. That collection is preserved by phi. So when you apply phi to K, what are you going to get? Well, the image certainly lies inside the subfield. So phi maps F to F also, its identity on F. So F goes to F and the roots of Fi map back to the roots of Fi. So it's just the subfield generated by F and, well, again the roots of Fi. Okay, but that's exactly K once more. Okay. So if you look back, it's the same proof really for the uniqueness as well. So phi K is a subset of K, and now we repeat the argument with phi inverse in place of phi, repeat with phi inverse in place of phi, and well, when you do that, what do you conclude? You conclude that phi inverse of K is a subset of K, and therefore phi K is equal to K. Okay, and that's exactly what we needed to prove in part 2 of this proposition, that phi, whenever you take an automorphism, an F automorphism of L, then K is preserved by that automorphism. Okay, so that's 2 parts of what we need to show. 3 implies 1, 1 implies 2, and let's finish this off by showing that 2 implies 3. So what does this mean? We have to assume part 2, which means that this stability under automorphisms, under F automorphisms, and we need to show 3, which is that every element alpha, so take an element alpha in K and look at its minimal polynomial, be its minimal polynomial over the base field F. Okay, so in other words, this is an irreducible polynomial, irreducible monic polynomial satisfied by alpha coefficients in F. Now we need to show that M alpha splits completely over K. Okay, so let's assume the contrary. Suppose M alpha of X does not split. Now what does that really mean? Well, it says, so remember L is the algebraic closure. I have K, I have F. Now I have this polynomial M alpha, and there is an element alpha in K, right? Alpha is the element I started out with. The polynomial M alpha of X, well, that's got coefficients in F, so maybe I'll write it downstairs. M alpha of X is a polynomial with coefficients in F. M alpha has certainly one root in K, right? Because alpha is certainly a root of M alpha. But what we are assuming here is that M alpha does not split over K. In other words, when I write out the factorization of M alpha of X into a product of irreducibles over K, all factors are not linear, right? I don't get n roots in K. So not all roots of M alpha lie in K. So some roots you will only see in higher extension fields. Okay, so in particular I will certainly find all n roots in L for sure, right? So let's go to L so that M alpha splits completely there. So since L is algebraically closed, here's what I know. M alpha of X will certainly be, I can write it as X minus alpha 1, X minus alpha 2. So I'm just going to assume, M alpha is of course monic here because it's the minimal polynomial. For some alpha 1, alpha 2, alpha n coming from the algebraic closure. Okay. Now let's assume that the first root alpha 1 is alpha here. That's the alpha I began with. So let's call alpha 1 as that alpha. Now the assumption we have made, M alpha does not split completely over K, means that at least one of these alpha i's is not in K. Okay, so by assumption, so maybe I should call this something star by star, there exists some alpha I which is not in K. Okay, so let me just call it alpha 2. Say, let's just renumber our alphas if necessary and say alpha 2 is not in K. Okay, so alpha 1 is in K, but alpha 2 is not in K. Okay, and that is somehow the key point here. So I have L, K, F, and the situation is I have one root in K and I find another root which is not in K, but sort of outside K, it's only in L, for example. Okay, whatever it is, it's not in K, it's outside is what I mean. Now this is going to be what we will use in order to get a contradiction. We will contradict the hypothesis 2. Okay, and what did the hypothesis say? It said that every homomorphism, let's go back and see, every homomorphism or automorphism of L which preserves F pointwise must map K to itself. Okay, now because we now have alpha 1 in K and alpha 2 which is not in K, let's sort of use these two guys to define a homomorphism. Okay, so the idea is to try and define a homomorphism which will map alpha 1 to alpha 2. Okay, if you can do that, then we would have somehow gotten a contradiction to 2. Okay, so that's what we'll try and do now. Okay, so So again, recall from the previous or initial discussions on adjoining, symbolic adjunction of roots and so on, that if alpha 1, so since alpha 1 and alpha 2 are both roots, well, they both have the same minimal polynomial, over f, right? Because of course, what is the minimal polynomial? What we called m alpha of x. Both of them are roots of that, and m alpha is irreducible, so it must be the minimal polynomial of alpha 2 as well. Okay, so since they both have the same minimal polynomial, we know that there exists an isomorphism of fields, okay, from where to where? From f adjoint alpha 1 to the field f adjoint alpha 2. Okay, and you can either think of this symbolically. So what is so I want to say think of all this sitting inside L, for example. Okay, for the moment forget K. So there's F here. So we'll bring K back into the picture afterwards, but for now just look at f alpha 1 and f alpha 2. What we know is that there is an isomorphism between f alpha 1 and f alpha 2, okay, which is identity on f. So there is an f isomorphism. Okay, let's call this map phi. There exists an isomorphism phi from f alpha 1 to f alpha 2. Okay, so recall this statement. So recall from the initial discussion on adjunction and so on. Okay, and if you quickly recall why this was the case, because in fact both of these fields are abstractly isomorphic to the field fx, the polynomial ring, modulo the ideal generated by m alpha of x. Okay, m alpha x is a maximal ideal here, and so both these guys are actually isomorphic to this abstract field fx modulo m alpha x. Okay, so that's how one sort of deduce that. So there is an isomorphism further with an additional property such that it maps alpha 1 to alpha 2 with phi of alpha 1 equals alpha 2. So this is the key property that we will use now. Okay, so I'm guaranteed that such a map exists. Now, so this is sort of the first statement to recall. Now, the second statement, given an isomorphism, so given an isomorphism from one field to another, this case f alpha 1 to f alpha 2, so I am given an isomorphism of fields, then it extends to an isomorphism of their algebraic closures. Okay, now in this case L is the algebraic closure of both f alpha 1 and f alpha 2. So the universal property says that phi extends to an isomorphism of L, okay, to an automorphism of L if you wish, because in this case I have taken L to be the universal, to be the algebraic closure on both sides. Okay, so given an isomorphism phi from f alpha 1 to f alpha 2, there exists phi tilde from L to L such that phi tilde, when you restrict it to f alpha 1, it coincides with the map phi. Okay, so this is the other property that we need to recall from the construction of algebraic closures. But now observe that this exactly contradicts the hypothesis 2. So now observe that this map phi tilde from L to L, it's an automorphism of L, does the following. It maps, well, it coincides with phi on f alpha 1. So this just does whatever phi does to alpha 1, and remember that's the special property of phi that we talked about, is that it maps alpha 1 to alpha 2. Okay, so phi tilde maps alpha 1 to alpha 2. In particular, recall we assumed that alpha 1 was an element of K and alpha 2 was not an element of K, right? This was our assumption, right? So this is what we had assumed. So our assumption was that this happens. So what does this mean? This says that phi tilde, therefore phi tilde of k is not k, right? It's mapping one element of k to an element that's outside k. Okay, and so this contradicts our hypothesis 2 and completes the proof of this proposition. Okay, so normal extensions are, well, they can be thought of as splitting fields of collections of polynomials, but in terms of homomorphisms, they are also sort of the extensions with the property that automorphisms of the algebraic closure always leave normal extensions stable. They fix them. Okay, automorphisms which are identity on the base field. Okay, and so in some sense the remarkable point, one other little remark here is that this last point here is also rather remarkable. It says that if your extension is normal, so it's the splitting field of a collection of polynomials, then every alpha in the field has a minimal polynomial which also splits completely. Okay, which means that if one root, I mean alpha is of course one root of its minimal polynomial, what we are saying is that all the roots of that minimal polynomial must actually belong to the field k. Okay, and so that's somewhat remarkable. So for example, if you recall the example of a normal extension we gave, if you take the field q and adjoin both root 2 and I to it, okay, think of it as a normal extension of q. So of course, we exhibited those two special polynomials for which this is the splitting field, but the third equivalent property of this proposition says you can in fact take any alpha you want in this field k. Okay, for example, I can take alpha to be root 2 plus 3i. This is an element of k, right? Or in fact more general combinations if you wish, say 1 plus root 2 plus 3i is another element. So suppose I pick this element alpha in my field k, then what it says is you look at its minimal polynomial m alpha of x over q. Okay, so this is the minimal polynomial of alpha over q. Then all roots of this minimal polynomial will also lie in this field k. Okay, so all roots of m alpha x lie in k. Okay, so or in other words, the minimal polynomial splits completely over k. That's what I mean. Okay, so that's somewhat remarkable because what it says that the other roots, or sometimes we call it the other conjugates of alpha, right? The other roots of its minimal polynomial are also somehow combinations of root 2 and I, for example. That's what this proposition is saying. Okay.